consider SEIR model. And like I said the computational techniques is similar, regardless the complexity of the model you are considering. However, sometimes the approach may be different. For instance, by the time you begin to extend the SEIR model to, for instance, SEIR, SEAIR, compartmental models and the likes. So one may want to take a different approach to obtain the equilibrium point of such model, particularly the endemic equilibrium. So I will try to manage my time as much as I can, because we have at least two other concepts that we're supposed to take a look at, which are the computational techniques for reproduction number and the local stability analysis. And I will also make use of the board as much as I can. You can remember yesterday that I said one of the reasons why we have to find equilibrium points of compartmental models is that if you are able to understand the equilibrium point, it will help us to predict how the system will behave over time. So that's one of the key things, that why we need to examine the equilibrium point of a model. Also, it will also help us to determine to analyze the stability of the system, because this is important, is very important. So I will just go through. We were able to look at finding the endemic equilibrium point of SEIR model yesterday. So, and I pointed our attention to a particular term, which is highlighted red here. I said something about this, that threshold, if that value is less than 1, we are going to get negative result, right? So it means that the positivity of this solution depends on the bound of that expression. It will mean that before we can have that endemic equilibrium to be positive, we must have that beta lambda over mu into sigma plus mu. I hope I got it right. Must be what? Must be greater than 1. We now need to know what this guy is. It's a threshold, just like I said. We need to know what this is. And every compartmental model has a similar threshold. So if you have a compartmental model, for instance, SEIR, by the time we extend this to SEIR, SEIR will also have a similar threshold. Okay, so we must have that threshold to be greater than 1 for that solution to be equals to be positive. Okay, so going through the similar process, we can also find the equilibrium point for SEIR model. I will not take my time on this. I will just scroll through to see the solution. So if you have a SEIR model, you will observe that, like yesterday, we have the I dt to be equals to beta is minus, do we have minus gamma plus mu I, right? And at the steady state, this is equals to 0, isn't it? We were able to solve this directly because the two terms, I is a common factor. And we know that the product of two terms is equals to 0, if either one or two of them is equals to 0. We were able to get S directly from here, isn't it? But when we look at the case of SEIR model, if you look at that, what is contributing to the complexity of the nonlinear model is that nonlinear term, which is beta Si, isn't it? When you look at it in this case, we don't have any common factor. Do we have common factor there? In the dt, Look at the heat dt. E is not common because we have beta is minus sigma plus mu e. Isn't it? If you look at this, it's not common. So if you have this similar, in this kind of situation, one of the first thing we can do, can I have the slide back? Like I said, I will not take more time on this. So if I have this at steady state, we agree that this is what we are going to have, right? Who does not agree with this? So let me know. I don't agree that at steady state, the model becomes this. Let me see your hands up. Do we agree? Okay, so at steady state, we are going to have that model 2 becoming this. So we see that when more compartments are introduced into the SEIR model, solving the new model explicitly or directly in terms of the model parameters requires high computational effort. That's if at all is this even possible. It is not always the case you can explicitly find the endemic solution in terms of the model parameter. So in such case, expressing the solutions in terms of the force of infection is a good alternative way. So in order to simplify this steady state system, we can represent the system in terms of force of infection. And like yesterday, what did I call the force of infection? Lambda is equals to what? Beta I, right? It will mean that wherever I find beta I will put what? I will put lambda. If I do that, then I'm going to have this system. Do we agree? We all agree that from system 3, we are going to have system 4. If you put lambda is equals to beta I. So if you have that, then we can easily solve from equation 1 to 4. We can easily solve that system 4 from equation 1 to 4. Can somebody tell me the solution for equation 1 in terms of S? If you solve the first equation here for S, we are going to have what? We are going to have S star is equals to lambda over lambda plus what? Plus mu. Thank you. This is what we are going to get. So if you look at the second equation, we can find E in terms of lambda as well, since we'll be able to know the value of what? The value of S. Is that clear? So from 2, we are able to get E. Moving on to the third equation, we are going to get what? I. If we move into the fourth equation, what are we going to get? We got R. Solving all the equations in the new steady state system 4, starting from the first equation to the last one, we are going to get this. Do we agree with this solution? It's straightforward, isn't it? The solution is straightforward. You get S from the first equation, you get E from the second equation by substituting the value of S. Isn't it? Then you move on to the third equation to get your I by substituting the value of E. So moving on then so we have this. This is the general solution to that steady state system 4. Right? So now from here, we said that the transmission of a disease is defined by what? What is the transmission of a disease? The transmission of disease, according to this model, is defined by what? Beta I. Right? So if you have this force of infection to be equals to beta I, it will mean that when lambda is equals to 0, implies that I is equals to what? I is equals to 0. If I is equals to 0, it means that lambda will be, if you have lambda to be equals to 0, can I have this slide? So if I have lambda to be equals to 0, look at the first equation. If we put lambda to be equals to 0, what, okay, maybe as we read. The disease-free equilibrium associated with the SEIR disease model 2 can be obtained directly from the steady state solution 5 by setting lambda star equals 0, right? Thus, the disease-free equilibrium is given by, from the first equation, if you put lambda star equals 0, we are going to get what? Lambda over mu. If you put lambda star equals 0 in the second solution, what are we going to get? We get 0 ditto to the fourth and the third and the fourth solution. So that will lead to having the disease-free equilibrium as given in equation 6. Is that fine? Okay, so from here we may move on to find the endemic equilibrium. So we need to find the endemic equilibrium such that the endemic equilibrium of model 2 can be obtained by first substitute the appropriate result in 4 into the force of infection as steady state and simplify. Hence, you know, we have that lambda star is equals to beta I star. Permit me to retain lambda equals lambda star and I equals I star. If I retain that, I have this such that lambda is equals to beta. What is I? Can I have the result for I from the slide? I is sigma over lambda into sigma plus mu into gamma plus mu. Please let me confirm this. Okay, into lambda plus mu. Okay, thank you. So this is the I star. It means that this is equals to I star. If I substitute this here, so I have lambda here, I also have lambda here. It will imply that sigma plus mu into gamma plus mu into lambda plus mu is equals to what? Is equals to 1. If I have that, I can easily have sigma plus mu into gamma plus mu lambda is equals to 1 minus sigma plus mu and gamma plus what? Plus mu. This comes here, and this will be, okay, this becomes beta sigma lambda. So I will have here to be beta sigma lambda minus this. Thank you. Are we together? So I'm interested in making lambda the subject of the formula so that lambda is equals to beta sigma lambda over sigma plus mu into gamma plus mu minus sigma plus mu into gamma plus mu over sigma plus mu into gamma plus mu. Right? Where? Oh. Okay. There is this mu is missing. It will be here, isn't it? It will be here. We should have mu here. Thank you. So if you have that, we are going to have this. It means that these terms will cancel out. I will have beta sigma lambda over sigma plus mu into gamma plus mu minus what? Minus mu. Are we there? So since I'm always interested in finding a situation whereby the solution will always be positive, I can simplify this further to have my lambda be one over mu into bracket beta sigma lambda over okay. We suppose this should be like this, right? Sigma plus mu into gamma plus mu minus 1. But I want to think that we lost something in the process. Can I see the slide, please? The slide. So I lost. Okay. You remember when we included this? Okay. So it's supposed to be, thank you. It's supposed to be mu outside, then it will be 1 over mu. Thank you. So I can see. So that will lead us to getting that result. So having gotten our lambda to be this, what do we need to do? We substitute the result in 7 back to the solution we have in 6. Can we see the result? So if you do that, we agree that our lambda star is this. And we must make sure that lambda star is a positive. Are we together? So for this to be positive, it will mean that the term, the expression highlighted right there must be what? Greater than 1. Okay. So from here, we saw it should be noted that the expression highlighted right in 8 is an important epidemiological threshold associated with the disease dynamic described by model 2. This will be discussed in detail later. Finally, the endemic equilibrium of model 2 is obtained by substituting the result in 8 into 5 as, if you substitute what we have there into 5, and we are going to have this. You will recall that S star is equal to lambda over lambda star plus mu, right? So wherever we find lambda star, we just put that result. So from this result in 9, it is implied from 9 that the expression highlighted red in 8 guarantees the existence of positive or negative, which is not biologically reasonable, endemic equilibrium point of model 2. It means that we can have positive and negative results. But if you have negative result, does that make sense to us? It does not make sense. Because why? All the model parameters are what? Are positive, and we are dealing with population, either human or any population. So we want to move on to quickly look at what is that threshold that I've highlighted red in both model 1, model 2. But before now, we were told to know the importance of a particular concept in epidemiology, which is what? Basic reproduction number. So, and we know that basic reproduction number is helpful to measure how fast the disease will spread. Are we together? And this may also help us to determine whether the disease will eventually become endemic or epidemic. Okay. So, sorry, that should be R naught. An R naught of 2, if you have R naught of 2, implies that on average, one infectious individual transmits the disease to 2 susceptible persons, each of whom transmits to 2 others. That's just an assumption. It's just like the case of a Italian guy. When the guy came to Nigeria, which is an index case, is the red one there. It is assumed that the man transmits the disease to at least 2 persons, and the spread tree continues to grow in that order. Okay, so we will see that. Why is it? So we will see that it is important for us to study this threshold, because it tells us, it means that if you look at this generation, if you look at the 3rd generation, the infection has already reached to how many people? It has already reached to 8 people. So it will mean that we can quickly halt the spread of the disease by doing something that affects the reproduction number. So R0 as a threshold parameter has biological implication. It has a biological implication. If R0 is less than 1, it will mean that each individual on average will generate a secondary case of less than 1, isn't it? That is, there will be a secondary case of less than 1. And if the R0 is equal to 1, it means that what? The disease remains stable. With no increase or decrease in cases over time. Whereas when R0 is greater than 1, an infectious person will produce on average more than 1 new infected individual, and then the disease can spread in the population. So it will mean that if you have this information, it is crucial to the policymaker to intensify the effort that will reduce R0 below what? Below 1. It is important to intensify effort that will reduce this reproduction number below 1. So one other beauty of R0 is that we can also use it to determine the herd immunity. Prof mentioned this yesterday. So from here we can know the percentage of the population that do need to be vaccinated for the disease to be eliminated in the population. Herd immunity is a form of indirect protection from infectious disease that occurs when a large percentage of a population has become immune due to vaccination. You know, we cannot say that because vaccination is good for in fighting against any disease, we want to vaccinate the whole population, particularly like Nigeria, where we have a high population density. So, however, we need to know the percentage of people that do need to be vaccinated. So, as such, we can make use of this concept to be able to know the percentage of people that one needs to be vaccinated. And for an illustrative example, if R0 is approximately 5, it does mean that measles with R0 of up to 20 requires around 95% vaccine cover for elimination, while smallpox of R0 approximately 5 requires 80%. Where is that information coming from? If you put R0 to be equals to 5, we have 1 minus 1 over 5. We are going to get that to be 0.8, which is equals to 80%. So it means that we must be able to vaccinate up to 80% of the population in order to arrest the further transmission of the disease in the long run. Okay? So, for simple model, we can easily determine basic reproduction number. But as the model becomes complex, as we want to capture more reality into the dynamics of the disease we are studying, that may not be possible. So, but however, we may want to identify the factors that are determining the reproduction number. I'm sorry for the way the slide is displaying. The problem was from my system. So R naught is determined by three factors. We have the contact rate, which is denoted by P. We have the transmission probability. Okay, let me say this is C. This is denoted by this. And also we have infectious period. Infectious period. Let me call this D. So, transmission probability. Okay. P. So, if I have this, it will mean that R naught is the product of C, P, and what? CP and D. And you know, like yesterday we said that beta that we saw in the transmission there is a product of two things. It will mean that the product of this and this give what? Accounts for beta. The product of contact rate and the transmission probability is what is called giving us the transmission rate. So we have that. So this is the schematic illustration of what I've just said. The basic reproduction number, which is denoted by R naught, is the product of the probability of infection and the contact per unit time, and then the duration of infection. Keeping this definition in mind, if you have a simple model, let's say SEIR model. So you recall that lambda, the new case of the disease is defined by what? Beta high S, isn't it? And this will happen. We just need this to happen with an index case, isn't it? We just need this to happen with an index case. So if you now put I equals 1, because we are looking at the secondary infection, if you put I equals 1, we are going to have beta S star, right? We are going to have beta S star. This is CP, right? This is CP. Then we need the duration, right? So what is the duration of infectious person in SEIR model? Can we remember the time it takes person that eventually becomes infectious to leave I class? You know, the T is equals to beta IS minus what? Minus gamma plus mu, right? Is that? Minus, no, it will not be minus mu I. It is gamma plus I, mu I, because there is a recovery rate, isn't it? Then the person become recovered, the RDT is equals to what? Gamma I minus mu R. So it will mean that the duration of infectiousness of this person is on average the time to recover, isn't it? Which is equals to what? 1 over gamma. That is the period, 1 over gamma. So at disease-free state, when there is no infection, but in the presence of just one case, what is S star? Our S star is what? Lambda over mu, isn't it? So that we have this becoming beta times lambda over mu times what? Okay. Okay, the period, sorry. This one would be supposed to be, where is it? 1 over gamma plus mu. Sorry about that. You know, so the period, you know, in the process, not everyone may recover. Some may die due to the disease. So this would be 1 over gamma plus mu. So that if you simplify this, we are going to have beta lambda over mu into what? Gamma plus times mu. So if you look at SEIR model that we presented yesterday, this will be the term that I highlighted yesterday. Or is it different from that? So that means this threshold that guarantee the positivity of solution of endemic equilibrium is regarded as what? As R0. Do we agree? It's regarded as R0 associated with that model. So we can use the same approach to this is what I was explaining. If you look at this, if you have R0 equals beta S times 1 over gamma, that is for SEIR model without what? Without demographic. That will be for the first term here is beta. Here we have it to be beta times S0 times 1 over gamma, because there is no recovery, the demography in that model. But in the case of SEIR model with demography, you can see in that flow chart, there is no demography. That's why the product here is equals to 1 over gamma. But in the case of the SEIR model with demography, we are going to have it the way we have it on the board. So, but this can be done just for a simple model, just like I said. But when the model becomes complex, there are different techniques that we can use to calculate basic reproduction number. So when model gets more complex, R0 may become difficult to derive directly from the transfer diagram. Other methods to compute R0 include, we can use Jacobian method. Another method is the next generation method, and we can also use survival function method. But basically for this discussion, I'm focusing on the next generation method. So we will see how we can use that method even to derive the reproduction number that we have just gotten when we use direct observation from the flow diagram. Okay? So, in order to use the next generation method, there is need for us to divide the compartment into two broad categories. One, we must find the infected compartments and the non-infected compartment. So, look at the word, infected compartment. In the case of SEIR model, what is the infected compartment? Is I. In the case of SEIR model, what is infected compartment? E and I. So thank you. So we have E and I. So I will quickly run through the. So like I said, let's say we take SEIR model, for instance, the SDT is equals to lambda minus beta IS minus what? Minus mu S. Then the E, the T is equals to beta IS minus sigma plus mu A. Then the I, the T is equals to sigma E minus gamma plus mu I. Then the R, the T is equals to what? gamma high minus what? Minus mu R. So if I want to identify the infected compartment here, just like you said, I will concentrate on what? On E and I. So if I have those two compartments, then by next generation method, I need to redefine this system, the E, the I, in the form the X, the T is equals to F of X minus V of X. Are we together? So if you look at this now, where F is the factor having the new infection as entries. If you look at the first equation, do we have new infection here? What term is that? Beta high S. So it will mean that I can put that in this form such that I will have the E, the T, the I, the T to be equals to what? Beta IS 0 minus into what? Minus sigma plus mu into he. Right? Let me remove this. Then this is 0. I will have okay, if I keep minus out, this one becomes minus sigma E plus gamma plus mu high, right? Is that correct? Is that correct? Okay, this will not be here. You know there is minus here already. If you want to define it in this form, the minus, if you have minus, a term with minus sign, it becomes positive. The one with positive becomes what? Becomes negative. So I'll be able to find this column F to be what? Beta IS 0 and then V to be what? Sigma plus mu E and what? Minus sigma E plus what? Plus gamma mu. So if I have this, so the next thing is to find the Jacobian of each of these. We are all familiar with Jacobian matrix, isn't it? Jacobian matrix. So Jacobian matrix. So it will mean that we want to linearize this. We want to linearize this. Are we together? You know we have this to be non-linear term, this beta IS. So we want to linearize this so that we have so that we are going to have the matrix of new infection terms, which is F, coming from this, will be the partial derivative. If I call this to be G1, let me say I call this G1, I call this G2. Are we together? I will have the partial derivative of G1 with respect to E and the partial derivative of G2 with respect to what? With respect to I. Then I will have the partial derivative of G2 with respect to E, the partial derivative of G1, G2 with respect to I. Why is it partial derivative? Because we have this linear term, isn't it? So from there, if I do that, what did I call G1? Beta IS. Do we have E there? We don't have E. So that means the partial derivative of G1 with respect to E will be what? Will be 0. The partial derivative of G1 with respect to I will be what? It will be beta S. The partial derivative of G2 with respect to E is what? Is 0. The partial derivative of G2 with respect to I is also 0. I hope you are all together. Who is not with us? So, we have identified infected classes, isn't it? Which we called E and I, right? So we brought out those compartments and we expressed it in this form. We are now saying that we will linearize this, each of these factors, with respect to those two variables, which are what? E and I. So I now said, let this term be represented by what? By G1, because it is a function. And this one is also, we assume it to be a what? To be a function, which is equals to 0. So it will mean that we are now going to find the partial derivative of G1 and G2 with respect to E and with respect to I. And when we do that, we expect to get 2 by 2 matrix. So if you do that, the partial derivative of G1 with respect to E, in G1, we don't have E. And when you differentiate a function with a non-existing independent variable, it becomes what? It becomes 0. That's why we have 0 here. Then the derivative of this with respect to I, it will mean we keep beta and S constant. Then we differentiate I. And when we differentiate I, we get what? We get 1. Beta S times 1 will give us beta S. Since this one is 0, derivative of 0 to any variable is what? 0. So that's why we have this to be 0. Here is also what? Is also 0. So in similar way, we are going to do that for the other vector component there. Oh, dropped it. So if you do that for the V, we are going to get the, I call this also, maybe I call it this F1, and I call this what? F2. So maybe I should quickly run this up through the slide. Let's see. So we have this. Then we are going to get our F and V. Look at it. The F1, the E, the partial derivative of this, I think is the same. So if you look at this, the next thing we have not done here is that what? We will now evaluate this F at what? At disease-free equilibrium. We evaluate it at disease-free equilibrium such that wherever we find S become S star, which is equals to what? Lambda over mu. If you put S equals lambda over mu, are we going to have the result different from what we have there? It will be the same thing. So, hello? Can I have this slide? So we are going to have that. Then if you do the same thing, linearize this, we are going to get the result we have there. We have the result here. So the next thing is now to determine the reproduction number, which will be the characteristic. What do I do? Okay, I'm sorry, let me quickly round up this part. So, we know by definition of reproduction number through next generation matrix is the dominant eigenvalue corresponds to the matrix FV inverse. That is the spectral radius of this next generation matrix. If we are able to find this matrix and we are able to determine the dominant eigenvalue of this matrix, then we can deduce from that what our basic reproduction number is. So if we do that, we have the product of F and V inverse matrix. Can we still remember how to find the inverse of a matrix? Okay. So if we find the inverse of V matrix and we find the product of the two, we are going to get what we have there. So if you have the result, please let me quickly copy that. We have FV inverse to be equals to beta lambda sigma over mu into sigma plus mu into gamma plus mu. Then beta lambda over mu into gamma plus mu. Then we have here to be 0, 0. So if you have this, it means that if I have FV inverse minus lambda equals to 0, that is, I want to find the eigenvalues of this matrix, which will mean that I have to solve this resulting characteristic polynomial. If I'm able to find these lambdas that are associated with this matrix, I have a 2 by 2 matrix. So how many eigenvalues am I expected to get? 2. If I get 2, I'm able to identify the one that is bigger than the other, then I can settle for that eigenvalues as the dominant eigenvalue to that which correspond to the reproduction number. Okay, let's do that together. So what do we mean? If I have my FV inverse to be this, what am I going to do to get this equation? I will subtract lambda from both the leading entries so that I'm going to have the determinant of beta lambda sigma over mu into sigma plus mu into gamma plus mu minus what? Minus lambda. Then I have beta lambda over mu into gamma plus mu. Then I will have 0, 0 minus lambda is equals to what? Is equals to 0. So that means this becomes what? So by the rule of, this is a determinant. I can evaluate the determinant of a matrix along any row or column. I may choose the second column, or the first column, or the first row, or the second what? Or the second row. But it is more convenient. Since I have this to be 0, I can evaluate it through what? Through this. So if I have by this I will have, if I have A, B, C, D, determinant of this becomes AD minus what? Minus BC. AD minus BC. What is A in this case? This one. This is A, this is B, this is C, this is D. If I substitute that, I'm going to have what? This times this minus this. It means I'm going to have the product of this, isn't it? So if I find the product of that, I'm going to have minus lambda times beta lambda sigma over mu into sigma plus mu into gamma plus mu minus what? Minus lambda is equals to what? Is equals to 0. So this can easily become lambda into bracket lambda minus beta lambda sigma over mu into sigma plus mu into gamma plus what? Plus mu is equals to what? Is equals to 0. If you have A times B equals 0, is either one is equals to 0 or both equals 0. It will mean that for this result to be equals to 0, lambda is equals to 0 or lambda minus beta lambda sigma over mu into sigma plus mu into gamma plus mu is equals to what? Is equals to 0. So we can solve this for lambda such that lambda is equals to 0, comma, lambda is equals to what? Let me say this is lambda 1, lambda 2 is equals to beta lambda sigma over mu into sigma plus mu into what? Gamma plus mu. So for me to now find my R naught, we said what? Is the maximum of what? Lambda 1, comma, lambda 2, which is equals to the maximum of 0, comma, this, which is equals to what? So which one? Is it lambda 1 or lambda 2? Maximum of, which is equals to lambda 2. And what is lambda 2? That is beta. So if you now look at the slide, can we see? Hello, please let me have this slide back. So if you look at this, for the endemic solution, look at this. Can we see? The expression highlighted red here is equals to what? Is equals to our R naught. It will mean that we can finally express that lambda there. We can finally express that lambda star to mean mu into R naught minus 1. That means as long as R naught is greater than 1, there will be existence of positive endemic equilibrium. So I would like to stop here today. I would not know if time permits, we can have a little more time on this. Thank you so much for your time.